Okay, so these are the transient response specification already seen by you. This is a time versus, you can see here, time versus the response. So the transient response is increasing like this, it's reaching the maximum overshoot, and after that there are sustained oscillations because of the imaginary part we will be having conjugate. Uh, we have complex number with a complex conjugate pair of roots. So imaginary part will be responsible for the sustained oscillations. For exponential decay, the real part will be responsible. So this is after some oscillations, it will settle down at final value. And we expect that C of infinity to be, this is the steady state value, but there will be some amount of error which is shown like this. See, you can see some error has been shown here, that is represented by ESS. And sorry, so we'll be having rise time from 0.1 to 0.9. This is the rise time. Then after that, second, okay, rise time. After the rise time, we will be having maximum overshoot, and then we will be having settling time. So all those characteristics we will be defining one by one. So this is the graph we have to look into. This is the rise time, this is the peak time, this is the settling time. This is the settling within the 2% of, within the 2% is here 0.9 and it's 1.0. If your response settles within these two straight lines, then that means it's the settling time, and peak time is the maximum time here. And then we have a rise time, it will start from some value 0.1 up to the 0.9, that's your rise time. So these are all, that's a C infinity is the steady state time, and maximum overshoot MP means that what was the overshoot? Finally, it has, the transient period has started from the, has started at a zero value, then it has it is rise to a value of some value was here. So when the first peak will be, it will reach to this within the 2% value, 1.02. So that will be called as a maximum overshoot. We will define it one by one. So these are the specifications. Sometimes you need to draw them. And also from this, we can, we have to infer some values also sometimes in the questions. So first definition which we'll be talking about is rise time. This is for the second order. First order we have already done. So rise time is basically one. What rise time is? Time taken for the waveform to go from, same definition, to go from 0 to 0.1, from 0.1 of the final value to the 0.9 of the final value. Final value is C of infinity. That's what 0.1 final value is C of infinity, 0.9 you can see it here. So this is the rise time we will consider from 0.9 is here, final value, 0.1 of final value. In between this is called the rise time. Just a second. Okay, this is your rise time. Okay. So rise time will be again writing. That will be denoted by TR. So time for time taken for the waveform to go from or rise from, what is one and the same, to grow from 0.1 of the final value, 0.1 of the final value to 0.9 of the final value. So that's the rise time. Very simple. 0.9 of final value, that's C of infinity, to 0.9 of final value is the rise time. Let's now derive the expression for this rise time. expression for rise time. Let's see what is the expression. Okay. Now we are talking about the step response right now. So the step response of an underdamped second order system is given by, we have derived it yesterday, is given by, we should memorize this value now, C of t response in time domain is 1 minus e raised power minus xi omega nt divided by under root of 1 minus xi square sine of omega n under root of 1 minus xi square t, this value has to be multiplied by t plus phi. And this expression, you know, is valid for t greater than equal to 0. Okay. Then also we know where our phi value we have also seen yesterday, where phi is equivalent to tan inverse of under root of 1 minus xi square divided by xi. Okay. Now let's say when this time, when t is equal to capital TR, that is capital TR means we are talking about the rise time. So it is denoted by TR here. So when t is equivalent to TR, then we know at that time response will be, time domain response will be 1, that we have already seen. So time domain response will be 1. Yesterday we have seen that. So in that case, hence what we are going to write, hence from this equation we are going to substitute this, hence C of t, let's call it equation number 1, substituting the C of t equal to 1, that means 1 will be equal to 1 minus e to power of minus xi omega nt divided by under root of 1 minus xi square multiplied by sine omega n under root of 1 minus xi square into, this whole will be multiplied by t. Okay, here we don't have to write, here we don't have to write this omega n into under root of 1 minus I square into t. Instead of t, what we will be writing now, we'll be writing tp. Here also tp, so we'll replace that when t is equivalent to tp. So we'll be writing here, sorry, tr, and then here also we'll be writing by tr plus phi. So this is very simple. Already explained that when C of t, yesterday we have seen the values of C of t equal to final response is equal to 1. So that value we are substituting here, and second order expression we are writing for the response, for the step response of a underdamped second order system. Okay. After that, what will go? This minus and 1 will get cancelled, and minus will go this side. It will become 0. So two quantities will be left. So leftover will be, or above expression will be e raised power minus xi omega nt divided by under root of 1 minus xi square and sine of omega n under root of 1 minus xi square into tr plus phi. Sorry, this I'm writing in, this is also tr. So this is the expression we will be having, that should be equal to 0. Now, since in this case either of them has to be 0, so this cannot be 0 because this is an exponentially decaying function. It is for minus xi omega n tr divided by under root of 1 minus xi square. This is not equal to 0. This cannot be equal to 0. So what can we expect? We can, out of these two, we can expect the sine value. That is, therefore, sine omega n under root of 1 minus xi square tr plus phi will be equal to 0. So this sine can be when 0. So when sine value is 0, so sine can have a value of number of pi's, n pi. So if n is, the n values will vary from 1, 2, and so on and so forth. So sine of any pi is 0. That we already know. You can see that we have seen from the sinusoidal curve also that sine of any pi is 0. So we can write this equation equal to sine of n pi. Sine and sine gets cancelled. So what will be left here? So left will be omega n under root of 1 minus xi square into tr plus phi will be equal to n pi. That will be equal to n pi, and value of n will vary from 1 to 2, 3 up to the higher numbers. But what we are doing here, you can see the graph here. From the graph, we can see that we are interested in the first peak. That means we are interested in the first attempt to reach the response from 0.1 times final value to 0.9 times. So between this, we are expected to interested in first attempt. That is, at first time we have, there can be number of peaks, but we are not interested in the second, third, fourth peak. We are interested in first attempt. In that case, n will be substituted equal to 1. So I'll write this point here. Since we are interested in the first attempt by C of t to reach the steady state value, n must be 1. N must be 1. So we need to get the value of n equal to 1. So therefore, what we can do here, can substitute it, omega n under root of 1 minus xi square tr plus phi will be equal to pi. Okay. So that will be equal to pi. Therefore, we can obtain the tr. Therefore, rise time can be obtained as pi minus phi divided by pi minus phi divided by omega n under root of 1 minus xi square. So this expression we have to remember for what? Sorry. This expression has to be remembered for the rise time. And we know, somebody can ask, what is the value of phi? That we already know here. The value of phi is tan inverse under root of 1 minus xi square divided by xi. That is, everything is in terms of the value xi. Okay. So this is the first expression. Sanjeev, it is okay?
Yes, sir. Clear.
Okay. So it's a very simple expression. You have to see from the graph also what's happening. That's why I have used this graph here. Okay. Next expression is for the peak time. The second definition for this is, these are very important expressions They will be used for the numericals also, particularly in the gate numericals. So second is peak time. Peak time we represent by TP. So what basically is the peak time? The basically peak time is the time that will be required by this response, that is a C of t, we have a response to reach the maximum or the peak value at first instant, at first time. That means at first instant we have to see. So somewhere we have to go to the peak value like this, and we will see the what is the peak value at this. So that's what we will be talking about. This is the peak value. So first instant, second instant cannot be taken. See, this is a first overshoot. Then this is first undershoot. This is first undershoot from here. See, please make sure that what are these undershoots and overshoots. Let me take this type of pen. Now this is your first overshoot. That means maximum value you have reached. Then we have gone down. So this is your first undershoot, first undershoot, then again it has risen. This is your second overshoot. So on and so forth, it will continue unless the oscillations will die down and we will settle down at some value. We'll settle down at the steady state value. Maybe there is error or there will be very small error, but we will settle down at some value. So these are overshoots and undershoots. Okay. Now with this peak time, so we will write the definition of the peak time as peak time is the time required it's the time required for the response to reach maximum or peak value at very first time or very first instant. Okay, this is the peak time. Okay, let's start deriving the expression for the peak time. So how we will be deriving the expression? So next is expression for the TP. Okay. This is expression. So next up, again, the step response of underdamped second order system is same. So we have to continue with all the expressions. So the step response of underdamped second order system is given by what is the value? C of t, again with same thing, 1 minus e raised power minus xi omega nt divided by under root of 1 minus xi square into sine of omega under root of 1 minus xi square into t plus phi, and we know this expression is valid for t greater than 0. Greater than equal to 0, this expression is valid. Okay. Also, where phi is equal to tan inverse of under root of 1 minus xi square divided by z. This is value. So how we obtain, if you go through your 12th class exam, 12th class, sorry, mathematics, we know that maxima and minima, this is the peak time, maxima. So maxima, minima we used to obtain by deriving the independent variable with respect to the, by deriving the dependent variable with respect to the independent variable, and then we substitute it equal to 0. That's how we get the maximum value. So we obtain the peak that you already know from the mathematics. We obtain peak time by differentiating c of t with respect to time and setting the derivative equal to derivative equal to 0. Setting the derivative equal to 0. Or we can write from above expression, let's call it one equation, dc of dt at time. What is the time? T equal to Tp, because we are finding peak time equal to 0. So we have to find this derivative with respect to time and then differentiate with respect to time and put T equal to Tp. So let us do it. So how we can, 1 will be 0. So these are the two expressions. UV function, that's a product function, is this one. So first into derivative of second plus second into derivative of first. That you know from the mathematics itself what we do. So or we can write, so in this expression we can write dc by dt of this will be equal to, if we go to this side, so this will be 0 minus, we will not be writing for the time being this one, sorry, this will not be writing, we'll just differentiate it and put it equal to 0. Now I need to write this one. So first is 0 minus, second function is, this is first function, it's first into derivative of second. That means we'll be writing e raised power minus xi omega nt divided by under root of 1 minus xi square into derivative. Derivative of sine is cos omega nt 1 minus under root of xi square 1 minus under root of xi square plus 5. Okay. So this into the internal differentiation, you can see sine internal differentiation. We are differentiating with respect to time. So omega n 1 minus xi square will also come multiplied by omega n under root of 1 minus xi square will also come into the picture. Plus, I'll be writing that here. Plus, second is what? Sine of omega n under root of 1 minus xi square. Okay, this is 5, please. Okay, 1 minus xi square. Okay. Okay, we have not written t here, sorry. We should have written t here. This t will be now Tp, sorry. Okay, t plus internal differentiation. Now, second is this one, Tp plus 5, second into derivative of first. Derivative of e raised power x derivative is same. So that will be multiplied by e raised power minus xi omega and Tp will be writing here. Okay. Divided by under root of 1 minus xi square into differentiation of this t with respect to t we are doing, that will be xi minus xi omega n, and that should be equal to 0. Let's substitute it equal to 0 because that's what we are told. We are differentiate this and substitute equal to 0. That's what we are doing. So in this case, you can very clearly see e raised power minus xi omega n t. Okay, omega n. So e raised power minus xi omega n t, omega n. So these terms are common. I think rest is not common. Rest nothing is common. So in first we can write minus 1 under root of 1 minus xi square into cos of this, because I'll be highlighting this because this term, complete term, is common in both. Okay, for your knowledge, this complete term is common. This is common here also, and this is also common in, it is common here also, and it is common here also. So I can take common them and they will become 0. So that's what. Okay. Or I can write here, or I can write minus under root of 1 minus xi square into leftover will be cos of omega n under root of 1 minus xi square into tp plus 5. So this will be leftover in first term. Second term we will have minus minus can be plus minus. Second term will be, okay, so plus, just a second, how we are getting, yeah, previous term will be minus. Okay, that is fine. So second term, yeah, this will be plus just a second, plus, and this will be, you are getting this and this and this is cancelled, so this will be xi sine of omega n under root of 1 minus xi square into again tp plus 5, and that you can substitute equal to 0. I think this is correct. It is for minus xi into internal differentiation is minus xi. Yeah. First, just let me check. 0 will be there. Yes. So minus is here. Yeah, minus is outside for both. So this will also be minus and this will. So don't get confused here. So this will be plus then. See here, actually I should have written it like this. And let me put the bracket here. Some people may get confused. Yeah, here, complete is minus. Okay, minus is for both the brackets. So when we will differentiate them, first term will become minus, second will become plus. That's all. Okay, let me add the page. So from here, I can write it like this. I want to just reshuffle it. I want to write it this way. Sine, I'll just reshuffle it. Sine under root of omega n, sorry, under root of 1 minus xi square tp plus phi. Okay. Sorry. Yes. So this was 500. No, can go. So 500 Okay. Okay, so this is sine. So xi I am writing here. So I'll be writing this like this. xi, I will put it like this here. So xi multiplied by this minus, so I will be writing under root of 1 minus xi square cos. I am just reshuffling them. Omega n under root of 1 minus xi square, okay, into Tp plus phi will be equal to 0. So this equation can be written. Second term I have brought it first, and first term I have brought it on the second position. Why I'm going to do this? I'm going to make sine A cos B, okay, sine A cos B. So this is sine A cos B minus cos A. I have expression like this, sine A cos B minus cos A sine B. So that expression is equivalent to sine A minus B. I'm trying to make it like this. So sine I have here, cos I will try to make xi. Cos phi is xi here. And then sine A cos B, this is cos A sine B. Sine B I will try to make, sine phi I will try to make under root of 1 minus xi square. Now I'll substitute these values in the above expression. So we will get sine A, that is omega n under root of 1 minus xi square Tp plus phi. This is sine A. And then instead of xi, I will write cos phi minus I am going to write cos A. Cos A is the same thing. Cos omega n under root of 1 minus xi square into Tp plus phi cos A sine B. This I am going to write sine phi will be equal to 0, or this expression can be written like this. So what we are going to get out of this is sine A minus B. So that will be A is omega n under root of 1 minus xi square. Sorry. Xi square Tp plus phi minus sine A minus B. B is also your phi. So that is phi. That will be equal to 0. So phi and phi gets cancelled. So, or we can write this expression as sine omega n under root of 1 minus xi square Tp will be equal to 0. So this can only be 0 when we have sine of n pi. So this is, we can write sine of n pi, where the value of n will vary from 0, 1, 2, and so on and so forth. So, but what we are interested in first peak. So let us cancel first sine n, yes, sine. So it will be omega n under root of 1 minus xi square Tp equal to n pi. So again, the same logic applies here also. What? Since we are interested in the time to reach the first peak, we are interested in time to reach the first peak. So therefore n will be taken equal to 1. So then what will be the Tp? Tp will be equal to pi divided by, Tp will be pi divided by omega n under root of 1 minus xi square. So time will be always in the seconds. So we have to always, this expression can be again boxed. Roll number 9, it is clear. 8.
Yes, sir.
Okay.
Clear.
These questions have to be memorized for the numericals, but very simple, simple mathematics of 12th class we have to use, and we can get these expressions. Okay, just a second. Now, next is maximum overshoot. Actually, I am today in the college, so I'm not comfortable with the setup. I had made a very good setup at my house. Anyway, we have to come to college now. So next is the maximum overshoot. Sorry. Maximum overshoot. Okay, this is the maximum overshoot. Let us see what is the definition and what's the expression for this one. So whenever we are talking about the maximum overshoot, we are talking about this from the graph. I have shown you already. This we are talking about this from the graph. This is the maximum overshoot. Okay, this is the tolerance value for the settling down of the response, and the maximum peak where we have that we consider the maximum overshoot. Okay, the maximum overshoot is what basically it's a closeness of the actual response to the desired response. What are the response we are getting? What are the actual response we are getting? How much close it is to the desired response? That is dependent by the maximum overshoot. But when it comes to the definition in context to the step response, then the amount of step response overshoots the steady state value. The step response will what? Overshoots the steady state value. You can see here, step response overshoots the steady state value. So how much this we consider steady state value, even though it's settling somewhere here, but because of the tolerance, settling time is considered within the 2% to stay within the final value. So how much amount, how much quantity the step response will move from this position, that is from the settling down value to steady state, from this peak to the steady state value. So that is called an overshoot in case of 100 amp second response. So we'll be writing that. First, we'll be writing that it is basically, if we talk about the practical terminology, it is closeness of the actual response to. First point is it is closeness of actual response to the desired response. Desired response, the closeness actual response to desired response, which is represented by maximum, which is represented by maximum overshoot, which is represented by the maximum overshoot. Then second definition according to step, it is defined as the amount the step response overshoots the steady state value. उससे ऊपर कितना जाएगा ये? Overshoots the steady state value or final value or final value at the peak time. expressed, how we express it, expressed as a percentage of, as the expressed as the percentage of the steady state value. Okay, it will be expressed in the percentage. Basically nothing but the maximum peak. You have to see the maximum peak. From that maximum peak, within the 2% of the settling value, top value, you have to see that's the maximum overshoot, nothing else. So mathematically, how we write it? Mathematically, this is represented by MP. MP is CTP. It's a maximum peak minus what is the final value, that is the steady state value, divided by final value multiplied by, you can multiply it by 100. Okay, now next is expression for MP. Expression for MP, that is maximum overshoot. Okay. Okay. So let's have an expression. So again, the second order system will be considering. When the second order underdamped system is excited, when the second order underdamped system is excited by, step response is 1 volt, by a step of 1 volt, the steady state value is also 1 volt. The steady state value is 1 volt. Okay, hence what we are writing here. So hence what will happen here? Hence MP will be C of TP. So we know that this C of infinity is equal to 1. Steady state value is equal to 1. So minus 1 we can write, divided by 1, we can write it simply minus 1. Okay, but where T is, we should have written it like this. Okay, fine. The same thing, C of T, we are writing at what? T is the peak value minus 1, since C of infinity, because final value C of infinity will be equal to 1. That value is equal to 1, excuse me. Okay, so this is what we are getting. Final value is 1, so this will be 1 and 1. So now again we know MP. How we can write now MP? MP will be equal to 1 minus, we have to write it, the second order response, where T will be equal to TP, e raised to power minus xi omega n, sorry, this is TP, yeah, not, yeah, TP at the peak value, sorry, TP sine undivided by under root of 1 minus xi square into sine omega n under root of 1 minus xi square into Tp plus 5 and minus 1. Plus 5 minus 1. This minus 1 is there. This is the value at T equal to Tp, maximum peak. So now in this case, what we'll be doing, 1 and 1 will get cancelled. substituting the value of TP because it's at the peak time. Substituting the value of TP peak time, which was pi divided by omega n under root of 1 minus xi square. So what we are going to get above, we have to substitute it in this equation. So 1 and 1 gets cancelled. Maximum overshoot will be 1 and 1 gets cancelled. So we'll be writing minus here, same, e raised power minus xi omega n. Instead of the t, we'll be writing pi divided by 1 minus xi square omega n is also here. Okay, then multiplied by sine omega n under root of 1 minus xi square. Tp is pi divided by omega n under root of 1 minus xi square plus phi. 1 is getting cancelled. Okay, 1 gets cancelled with 1. So omega and will go here. So mp can be written as mp will be equal to minus e raised power minus pi xi minus pi xi divided by under root of 1 minus xi square. Okay, because this will get cancelled, multiplied by this and this gets cancelled. So sine pi plus phi. Okay, sine pi plus phi. Sine 180 plus theta is sine theta itself. So we can write mp here as minus e raised power minus pi xi divided by under root of 1 minus xi square sine of 180 plus pi is pi. So from the damping ratio triangle, I can draw so this is your damping ratio triangle. From this damping ratio triangle, we had phi. This was 1. This was under root 1 minus xi square. You have to memorize these values. Okay, this is a damping ratio triangle. So you have to memorize this value. This is a simple value. Yes, please go ahead.
Sin 180 plus theta होता है minus sin theta.
Sin 90 plus किस कोऑर्डिनेट में आएगा? Sin 0 कोऑर्डिनेट में add sugar. Yes, add sugar तो हो गया, तो पॉजिटिव गया, कोई बात नहीं. We'll write positive. So that is my mistake. कोई बात नहीं. I have not seen this rather. So minus and minus will be plus, and we can change it here. No need. Sine of 180 plus theta is sine minus sine theta because it's in 180 plus is in third quadrant. Add sugar to coffee. Yes, fine. Okay, so this is fine. Damping ratio triangle is like this. So from damping ratio triangle, what we have? Call it question number 2nd. From damping ratio triangle, we know sine phi is under root of 1 minus xi square, whereas cos phi is xi. Okay. Okay, now substituting these two, let us say this is third equation and this is fourth equation. Substituting these two values, substituting the values of sine, we don't need value of cos. So mp, substituting second, mp will be e raised power minus pi xi divided by under root of 1 minus xi square. Okay, sine, oh sorry, I think just a second. Yeah, we have missed this denominator, I think. Yeah, this denominator we have missed. Why we have not included this? Where this has gone? TP, just a second. Yeah, we have missed this denominator. So this denominator will be there. So we can write it divided by under root of 1 minus psi square. I think nobody is attentive here. All are sleeping. So here this denominator will be there. I write it here now. Under root of 1 minus xi square. So that will be divided by under root of 1 minus xi square into sine phi. Instead of sine phi, we can write 1 minus xi square. So this and this will get cancelled. So therefore maximum overshoot can be written as E minus pi xi divided by under root of 1 minus xi square. Okay. Damping ratio triangle, we are getting this. So that expression. So this is the expression we need to box. This is a very good expression. Okay. Okay, is there any doubts up to here? Roll number 9.
No, sir.
Roll number 6. Is it clear?
No, sir, clear.
Rudba. Now, can you explain this graph to me now? Overshoot MP is a function only of damping ratio. You can see overshoot will not depend on anything. It will depend on damping ratio. I'll write it here for your information. Assalamu alaikum. Fourth. Time? Bas 15 minutes. So what we are looking here, that maximum overshoot will be a function of damping ratio triangle. Okay, so it means that the overshoot MP, it means that overshoot MP, okay, is a function only of damping ratio. You can see from the expression itself, there's nothing. Damping ratio xi. Okay. Now let's we can percentage. If somebody wants to take the percentage of this, then you can write MP is equal to E to the power minus pi xi divided by under root of 1 minus xi square into 100. Okay. So this expression is also valid. If you have to get percentage overshoot, you can use both the expression that you know. There's nothing. So now roll number 9. Can you explain this graph now? This is roll number 9. Are you there?
Yes, sir. Yes, sir.
This is MP. And obviously, this has to be a function of xi. So this is xi here.
Yes,
Maybe.
sir.
Okay, this is xi. So
Yes,
what's the meaning of this?
सर इसका मतलब है अगर डैम्पिंग ग्रेटर देन 1 होगी तो ओवरशूट 0 होगा.
Very good. If
damping 0 होगी तो maximum होगा.
If we are not damping the system, then we will have overshoot. जैसे अब practically मैं आपको कहता हूँ example. If you are going to become an instrument engineer or you are going to join somewhere in the multinational companies where you have lots of instruments to design, electrical engineer can also join there. Big companies are there. Emerson is there. Yokogawa is there. Then Anderson Hauser is there. These are multinational companies. So in these companies, if you go, you'll be asked to practically you'll be asked to program these instruments, and then you have to, once you program these instruments, then you have to not with a physical link, but with a soft link. You have to connect them with the control room. So while you are controlling these instruments, maybe there is a lots of hunting. Hunting means that your reading is not stable in the process. You have any type of chemical process, you can have food and beverage industry, you can have, and process fluid can be anything, and your process is not, you are not getting a proper reading. That means hunting is there. That means reading is not stable. Then what you do in that case? In that case, if your reading is not stable, so you will increase damping. But make sure that whenever you are increasing the damping, that should be within some specified value. What is recommended by the manufacturer or what is recommended by the guidelines there as per the plant guidelines. Because if you keep on increasing the damping, then the response will become slower. But then you have to draw a line where you have to increase the damping and then you can decrease this oscillations. So that's what is here. So as as the xi value is increasing, so what will happen? Your maximum overshoot is decreasing. That means you are increasing the damping. Once the damping is lesser, it will be high. I hope this is clear. Practical example I have also given. Is it clear or not? Rule number 9.
Yes, sir.
Okay. So next is the settling time. How much time we have? Actually, we don't have time. This is the problem. Okay, anyway. Settling time will finish this expression and then we have one. Next time will be. So next is settling time. Do you have today, Tanzim?
Yes, sir.
Time today, tomorrow, I don't want to take class because there is Salah and we are in always hurry.
सर आज हमें 5 बजे तक बराबर क्लास
कितने बजे तक?
बराबर 5 बजे तक
Oh, this is a problem. Okay. Now next is the settling time. Settling time is what? Again, this is a closeness of actual stress response to the desired response, as we have indicated already in the specifications earlier. I have told, but basically it is defined as what? It's the time required for the transient damped oscillations to reach and stay within 2% of the steady state value. So it is, we can define it. It is defined as, okay, the time required for the transient damped oscillation. That means transient specifications or transient transient time. Okay, it's a transient specifications of some response. So transient damped oscillations to reach and then to stay and stay within 2% of the steady state value. So it is just a time, but we have to see what type. This is for the transient specifications. Transient damped oscillations, when we start to move towards the steady state time, then it should what? Once we have passed this transient time, then it should stay and reach there and stay within the 2% of the final value. The final value means steady state value. You can see here from the specifications, you can very clearly see. See, this is the 1.02 can be also called as settling time. 0.98 can be within 2% higher or lower than the steady state time is called as what? We can see here. This is your settling time. TS is as a settling time. Okay. Okay. So what should be an expression for this one? Expression. And again, you have to remember this closeness. It's very important. The closeness of the actual step response to the desired response will be also included in this case. So next is as expression for TS. We call this TS as settling time. TS. Expression for TS. For the second order underdamped system with closed loop damping constant. That means it's having a damping constant. Okay. Xi omega n with a response described by, this is simply a second order underdamped system for a closed loop is there, we know that, but damping constant will be there. Let us see what is this damping constant xi omega n. So we know what is the response here. C of t in a second order is 1 minus, you have to memorize this now. It's a very important expression. Xi omega n t divided by under root of 1 minus xi square, okay, sine of omega dt plus phi. Omega dt, you can write it. Or you want to write omega n under root of 1 minus xi square. One and the same thing. T greater than 0, this expression is valid. Settling time occurs when, that is a, this time transient specification we have to see xi omega n t of s divided by 1 minus xi square, that should be within the 2%, so that is 0.02. Okay, settling time, we can take log of this one. Solving for TS. So we have TS equal to, I'll write the expression. You can take the log, so you can take log. This will go other side, log e raised power this, so that will be minus xi omega, and TS will be natural log of 0.2 into this, and that expression you can see. Minus natural log of, and that will be 0.02 under root of 1 minus xi square divided by xi omega n second. Expression second. So this expression is for the settling time. Now what's happening here? We can verify the equation from the equation number 2. We can substitute the various values. Okay. And we can see that numerator, if the numerator varies from 3.91 to 4.75, xi will vary from, so xi will vary from 0 to 0.9. If xi will vary from 0 to 0.9, then the complete numerator value varies from, I'm talking about the numerator value. So numerator varies from 3.91 to 4. And calculate 3.191 to 4.74. But then, as these things happen, you can substitute the various values of 0, 0.1, 0.2, 0.3. The value of the numerator will vary only from the 3.91 to 4.74. So then we approximately agree For what? Settling time as, so approximately settling time is considered as settling time that will be used for all values are settling time that will be used for all values of xi. So what we agree on? We agree on Ts is equal to 4 divided by xi omega n. So this expression has to be remembered for settling time. This is a very simple expression. So there can be lots of values, but finally we agree on the 4. So that's all for today. We have one delay time expression, then we can go for the numericals of this one. This is almost finished. All the theoretical part of this and expression part of this. Okay, Tanzib, you can send me the log. Okay. Tanzib.
Yes, sir. मैं उठा रहा था.
Roll number 6, is it clear?
Yes, sir.
Okay. Who else is there? Rutba, 27. Rutba, you have muted yourself. I'm not. She's not there. Only here. Rutba, I'm not getting your voice.
सर उसने टेक्स्ट किया शायद.
What's the problem? Problem क्या उसको? Audio में कुछ problem है?
Maybe, sir.
Okay, you can leave then. We will